Hello. Please open to page 5 in your absolute value packet. Page 5 in your absolute value packet. This is section 1, video 2, so we are finishing up the simplifying radicals expression. The objective is to rationalize the denominator and to simplify rational expressions with imaginary numbers. So we're going to talk about two concepts here, but again, they relate to the last video. So the first definition I want you to write down at the top of page 5 says rationalizing the denominator. Definition is the process of eliminating a radical from an expression's denominator. The process of eliminating a radical from an expression's denominator. What this says is when you have a radical expression, you are not allowed to leave a radical in the denominator. So the bottom of your fraction has to be a number. It cannot be a radical. For example, you are not allowed to have something such as 2 over the square root of 3. You are not allowed to leave a fraction like that. In other words, you're not allowed to leave an expression like that. So what do you do if that happens in a problem, which it will? So let's look at a couple examples. Letter A, we have 7 over the square root of 6. So we need to get rid of the square root of 6. Anytime you have a denominator with a radical, you need to multiply the numerator and the denominator by that radical. Here's why. If you remember from the last video, the product property of radicals tells us, let's look at the denominator first. This is kind of doing it backwards. They already split it up for us. So if we multiply two radicals together, you can multiply these 6's together and put them back inside the square root. So I'm going to write it like this just for this first example. What I mean by that is square root of 6 times 6. So let's leave it like that for now. The numerator, we just have 7 times square root of 6. You cannot multiply those further. You don't want to change it to a decimal. So leave it as 7 square root of 6. The denominator becomes square root of 36. The numerator keep as 7 square root of 6. So I hope you're saying to yourself, well, why is she writing all that? We know the denominator is just going to be a perfect square. So I'm going to circle that. The square root of 36 is 6. Numerator, again, stays as 7 square root of 6. That's our answer. That is completely simplified. That's how you write a rational expression without a radical in the denominator. So basically, just take whatever's in the denominator, multiply the numerator and denominator by that square root. Okay, let's try letter B. Okay, letter B, we have square root of 3 over square root of 5. Same process here. We are not allowed to have square root of 5 in the denominator. So take that denominator, multiply the top and bottom by square root of 5. Okay, let's start with the denominator. Square root of 5 times, square root of 5a times square root of 5a is square root of 5 times 5 is 25. A times a is a squared. So you'll notice on this example, I just went right to multiplying them together and writing out what the product was. So 5a times 5a is 25a squared. Numerator, you can multiply them together because they're both radicals. 3 times 5a is 15a. So leave that inside the radical symbol. Okay, let's put an equal sign. The square root of 15a, you need to ask yourself, is there a perfect square that goes into 15? Okay, I hope you said no. 5 times 3 is 15, and 15 times 1 is 15. So the numerator stays as square root of 15a, so leave that one alone. The denominator, the whole thing is a perfect square. So we can take square root of 25a squared, take the square root of each term. The square root of 25 is 5, and the square root of a squared is a. So our completely simplified answer here is square root of 15a over 5a. And again, always remember, this expression that we just simplified is equivalent to the original problem. All we did was get rid of the radical symbol in the denominator. That's all we did. Okay, let's go to letter F because this one's a little tricky. So I want you guys to try C and D on your own, and we are going to skip to letter F together because this one's a little tricky. Okay, so the ones we just did were basically the easy ones. So letter F, we now have a square root and there's a fraction in it. So we don't have them split up right off the bat. So the first thing we want to do is split up your fraction with the radical symbol in the numerator and in the denominator. So let's do this first. And yes, this will happen. You are not allowed to leave it like the original problem because that still means there's a radical symbol in the denominator. Now, little different. At this point, I hope you notice that 4 is a perfect square. And then square root of 75, we can actually simplify this. There's a perfect square that goes into it. It doesn't matter whether you simplify first or get rid of the radical in the bottom first, but I think it's easier to simplify first, especially if there's any perfect squares. So we can change 75 to square root of 25 times square root of 3, because 25 times 3 is 75, and we know that 25 is a perfect square. So all we did was simplify by finding the perfect squares. So I'm going to circle the 25. We know that that's a perfect square. Okay. Let's take the square root of 25, which is 5, and rewrite the square root of 3 in the denominator. Okay, we're almost done. What do you notice about this problem at this point? Okay, good. I hope you said there's a radical in the denominator. We are not allowed to have that. So you need to multiply the numerator and denominator by square root of 3. So what ends up happening here is we have 2 square root of 3 in the numerator. The denominator, leave the 5 there. Square root of 3 times square root of 3 is square root of 9. The square root of 9 is a perfect square, so I'm going to circle that. Rewrite our numerator, 2 square root of 3. And then our denominator is 5 times square root of 9 is 3. Now, yes, you could have done it all in one step. So 2 square root of 3 over 15 is our completely simplified answer. There is not anything else that you can do to make this more simple. Okay, so in addition to C and D, I would like you to try letter I. So go ahead and try letter I as well. And then when you come see me, make sure you let me know if you have any questions on that. Okay, we are going to skip that word problem for now. Let's go to page 6 in your notes. The last part of this lesson talks about imaginary numbers. So when you hear the word imaginary numbers, I know it sounds kind of weird if you've never heard of it before. This does not mean that you can't see the number, okay? And I'll show you when you could have an imaginary number in math. But there is such a thing as an imaginary number. Okay, so a quick definition, or I should say a short definition of the imaginary unit I is this. Anytime you have the square root of a negative number, that is represented by as I. The square root of a negative number is imaginary, okay? One application of this is when we graph quadratics, which you'll do with Mrs. Warnock in her enrichment chapter. If you graph a quadratic, okay, and it doesn't cross the x-axis, okay, here's our x-axis down here, that's because there's not an x-intercept, okay, they are imaginary. So it's one application of when you'll use or see imaginary numbers when the x-intercept does not exist. Okay, so that's our imaginary unit I. Let me just give you a little pattern here. If the square root of anything negative is imaginary, there's a pattern that this follows. For example, I to the 0 is 1. Okay, it's our imaginary number represented by I. Anything to the 0 power is 1. I to the first power is I. Now, if we have I to the 2nd power, in other words, if we go back to the definition that I wrote up here, if you square both sides of that, the square root goes away. So you end up with I squared is -1. And then one more number in the pattern here before it repeats. I cubed, to find what I cubed is, you need to multiply I to the 2nd and I to the 1st. Negative 1 times I is negative I. So this pattern actually keeps going. If we go to find I to the fourth, for I to the fourth, you can take I squared times I squared. Negative 1 times negative 1, we get 1. I to the fifth, you can take I to the third times I to the second. Negative I times negative 1 is positive I to the sixth, is negative 1. I to the seventh is negative I. I hope when you saw this pattern, I hope you noticed that it repeats. We could keep going, and the pattern goes 1, I, negative 1, negative I, just keeps going. So that's a quick explanation of an imaginary number. You cannot have a negative inside the square root. Just like with rationalizing the denominator, you cannot have a radical in the denominator. Okay, so let's do a couple examples here. We'll start off with one or two easy ones, and then I'll show you as hard as they get. Okay, so example 1. Very first thing you want to do is recognize the fact that there's a negative inside, and we want to split this up to be square root of negative 1 and square root of 49. Okay, we know that square root of a negative 1 is an imaginary number, and we also know that 49 is a perfect square, so I'm going to circle that one. Square root of negative 1 is I, and we know the square root of 49 is 7. So we want to write our answer as 7I. Typically, you'll see the I after the number if there is a number when you simplify. So that's all you do. That's pretty basic. So let's look at number 2. Number 2, square root of negative 33. We see a negative inside the square root again. So square root of negative 1 times square root of 33. First thing you should say is, okay, we have a negative. We know square root of negative 1 is I. Square root of 33 does not have a perfect square that goes into it. So you leave your answer as I times the square root of 33. So kind of makes it easy if there's not a perfect square that goes into it. It saves you some time. Okay, let's jump to number 5. Some of these are too easy. So let's jump to number 5. Okay, square root of negative 80x cubed. Okay, first thing you recognize is that there's a negative inside the square root. So we're going to write at least square root of negative 1. Next, I want you to ask yourself, okay, well, we have square root of 80 and square root of x squared. So I'm going to break these up using the product property of radicals. Square root of 80. There is a perfect square that goes into 80. And there's actually a couple of them. But I want you to think for a minute here, what's the largest perfect square that goes into 80? Okay, the largest perfect square that goes into 80 is 16. Okay, remember, if you're not sure, start dividing. Yes, 4 goes into 80. Okay, if you think there might be more, try 9, try 15. Sorry, try 9, try 16, try 25. Keep going, okay, until you think you found the largest perfect square. If you don't, you can use any perfect square. It just might take you more steps. We can then change x cubed, remember, to the largest even number, okay, times, in this case, x to the first, because we know any even numbered exponent is a perfect square. So make sure you change x cubed to be x squared times x to the first. We know square root of negative 1 is I, so I'm going to drop that down as I. I'm going to circle square root of 16 and circle square root of x squared. Square root of 16 is 4, it's a perfect square. Square root of x squared is x. And then leave the square root of x inside the radical because that is not a perfect square. Oh, it would help if I remembered 5, right? Sorry, guys. Square root of 16 times square root of 5 is 80. Don't forget about putting that 5 there. I realized I forgot that. So you need to also jot down that square root of 5. Okay, now you should write this in the correct order. Since the square root of 5 and square root of x are not perfect squares, okay, we can just rewrite those inside the radical, square root of 5x. The 4 typically goes in front, okay? and then the xi. Now, order does not matter, but normally you'll have that I at the end, okay, if there's a number or a variable in front. Okay, I hope that makes sense. We're going to try one more. So let's go to, let's try number 10 together. I want you to start it. I'm going to pause it for a minute. Okay, so I hope you have had a chance to at least start number 10. If you need to pause the video because you want more time to complete that one on your own and then check back for the answer, as always, that's a good strategy. So number 10, again, we realize that there's a negative inside the square root, so we know it's going to be an imaginary number. So let's break it down to square root of -1, square root of 75, square root of m to the 4th, and square root of n. Okay? At this point, we know square root of -1 is I. Okay? Anytime you have the square root of -1, it's I. 75 we can break down into two numbers, one of them being a perfect square. So hopefully you thought square root of 25 and square root of 3. I promise I won't forget the other number this time like I did in 5. 25 times 3 is 75, and 25 is the largest perfect square that goes into 75. Square root of m to the 4th is already a perfect square because it has an even number exponent. Rewrite square root of n. You cannot simplify that any further. At this point, I'm going to circle the perfect squares. So we have 25 is perfect, and square root of m to the 4th is perfect. So I'm going to keep that I right here. Square root of 25 is 5. Square root of m to the 4th, remember, just divide that exponent by 2. Square root of m to the 4th is m to the 2nd. And then the square root of 3 and the square root of n just stay inside the radical. You cannot simplify those any further. They are not perfect squares. Okay, so that ends the second video of lesson 1. If you would like to try another one or two of these on your own, feel free. When you come to see me for your second assignment of the first lesson, I will have my note answer key out in case you would like to check anything that you did try on your own. If not, please come see me for the assignment and to show me your completed notes. I can put your points in the grade book. Okay, I will see you soon.